This extraordinary machine, which is kept in the Science Museum in London, was built in the 21st century, but it was in fact designed 200 years ago. It was the brainchild of English inventor Charles Babbage, whose lifelong ambition was to design a machine that could create giant mathematical tables automatically. As I discussed with Professor Simon Schaffer, Babbage is considered to have invented the world's first computer, another milestone in our history of machines carrying out the functions of humans. And as so often with the history of artificial intelligence, what was meant to be a practical instrument soon generated the most extraordinary philosophical speculations.
Charles Babbage was the son of a Devonshire banker. He had a lot of inherited money to use. He was a brilliant mathematician. He was trained at Cambridge in mathematics at the beginning of the 19th century. He didn't take a degree because he refused to subscribe to the Church of England. He was a radical. He wrote on a huge range of topics, ranging from political economy and statistics to his loathing for street music and his admiration for Vesuvius. In the 1810s, when he was still a student, he and his friends at Cambridge were quite understandably concerned with the fact that the mathematical tables that they were using were full of printing errors. And Babbage realized that tables with printing errors could be actually lethal if these were the tables on the basis of which the position of ships at sea for English commerce relied. So he's alleged to have exclaimed, "By God, I wish these tables could be printed by steam." So from the 1810s, he set out a lifelong project to design and execute a machine that could calculate and print mathematical tables which were error-free. And he therefore devoted a huge amount of work to understanding what we would now call programming, computational design, statistical analysis, error reduction, the location of the sources of error, how to automate computation. And from the 1830s onwards, he had various versions of such machines. Initially a device that he called the difference engine, which is named after the mathematical principle on the basis of which the machine would execute its calculations. And then from the 1830s and 40s onwards, a much more visionary machine, which he called the analytical engine, which would essentially be a universal computer that would be capable of computing the value of any function and the value of functions in a grandiose and universal way. This is a device that was never actually completed. From the 1990s, a working replica of the machine was built and lives now in the Science Museum in London, thanks to Doran Swade and his collaborators, who managed to raise the funding to essentially build a difference engine. Partly it's a feasibility proof. It shows that Babbage was, in that sense, absolutely right. He could have built a machine that worked and did what he said it would do. Partly it's an object of wonder and admiration, and I mean it really is, because of its wave-like behavior and because of how magnificent the gearing is. But also partly to make one think hard about what is new about the analog and the digital and automation.
It's interesting that because at that time, those things that he was suggesting his machines would do were done by people. They were very human activities, were they not?
That's right. I mean, the word computer in the 1830s meant the humans, very often women, very often subordinate employees whose job was to do calculations. So right through this period, one of the most important books of tables, of mathematical tables in Britain, which was called the Nautical Almanac, which was the book of tables on the basis of which you could calculate longitude at sea. All those sums were done by humans, by computers who were paid from Greenwich by the superintendent of the Nautical Almanac. And you had men and women across the country who were sent sheets of paper from Greenwich with large numbers to calculate and turn into tabulated numbers on the basis of quasi-automated functions. And they'd do it by hand and by head, and they'd send them back. And what Babbage quickly realized, and I think this is crucial, is that the system of human management of humans computing obeyed the principles of division of labor that was common in political economy and in industrial manufacture. So that in order to get a reliable output, you could kind of treat the entire process as a factory of numbers, in which you broke down the tasks into simpler and simpler and simpler components, and then it would be relatively easy to verify and scrutinize how those components were functioning. Because secondly, Babbage realized that the success of such machines would rely on the ease and clarity with which you could police the processes that were going on. It wasn't enough to build a machine. You had to build a machine that was transparent enough so that it could check its own results. And that's what the principle of differences does. It breaks down multiplication and division into addition and subtraction, and it breaks those down into essentially the successive positions of a large number of metal gears, so that you could not only automate calculation, you could automate verification of calculation, so you could automate the output. And he was obsessed by that, and that's what fascinates me partly about Babbage, his obsession with checking, with verification, with maximizing the control over outputs. So, for example, one of the things he realized was that a major source of error in printed tables is, in the end, a human's got to read them. So what you need is a system in which reading errors, not just calculation errors, reading errors are minimized. And he reckoned that perhaps one of the sources of reading errors was the contrast between the color of the ink and the color of the paper on which the numbers were printed. So he ran the experiment of printing the same page of logarithms on 40 or 50 and then hundreds of different coloured inks and different coloured papers to work out which combination of this colour for the ink and this colour for the paper would minimise the transcription error. Right? And he worked out, I think it was black on yellow is the combination that is most easily, i.e. error-free, legible. Right? So the whole program, Babbage's whole enterprise, is simultaneously an enterprise that proposes to embody calculative intelligence in a machine and to make that embodiment transparent to vigilance, and to put those two things together in a series of engines. And he does use the phrase intelligence to describe what is going on.
Babbage's most important collaborator was a brilliant mathematician, Ada Lovelace, who happened to be the daughter of Lord Byron. She not only helped Babbage develop the programming for the machine, she engaged him in discussions about the profound philosophical implications of what they were doing. The most important question was, could it be said that the difference engine is in some sense thinking?
And what Ada Lovelace says is, no, you can't say that the machine is thinking because it can't anticipate. Because it's entirely reliant on its program. They don't use the word program, but it's clear, I mean, that's roughly what they're referring to. Because it can't foresee, it can only be programmed or set to deal with some future output. We can't describe it as thinking. So Lovelace certainly associates thought with the capacity of anticipation. Right? And for both Babbage and Lovelace, I would say, for both of them, the two key features that dominate their concerns with the machine are memory and anticipation. And there's almost a kind of theological aspect to this, magnificently. Because anticipation, Babbage shows, is essentially the mechanical explanation of miracles. So Babbage, in one of his more brilliant books, argues that, look, he could set the difference engine to print the same sequence of numbers for an indefinite length of time, 2, 4, 6, 8, 10, 12, for an indefinite length of time. And then he can program it in advance so that after the, say, 2000th number, the sequence suddenly changes. If you'd been watching the outputs, I mean, losing your will to live, obviously, but if you'd been watching the outputs and then suddenly it changed in a way that you could not have anticipated, you would call that a miracle. So Babbage is insinuating, it would be too dangerous for him to say this, but he basically says this, that what the Christians call miracles could be understood as changes in programming. Similarly, memory, for Babbage it's clear that memory is about the afterlife. That the world of punishment and redemption makes no sense whatsoever unless you can remember what you did. And Babbage associates memory with heaven and hell. That what heaven and hell are is essentially mechanical memory, right? And Babbage argues quite unambiguously in his autobiography that the air, which is a mechanical system, must have within it the trace of the structure of all speech that's ever been uttered, including, as he says very movingly, the screams of the enslaved people on the slave ships. So that for Babbage, memory is just the material traces of waves in the ether. It really exists physically. And it seems to me there's a very strong relationship in Babbage, certainly, between the capacities of the engines and this kind of moral, psychological, theological, call it what you will, model of the future, the past, memory, and prevision.
In the final episode of this series, Simon and I look at the origins of big data, another controversial modern technology with its roots in the early Industrial Revolution.
Just as there were massive and severe criticisms, protests, and resistance to automation, so there was massive criticism, resistance to data.
If you want to know when the next episode in this series is available, please click the button below to subscribe. Thank you.